Earlier classes you have solved differential equation by using either integrating factor for the first order differential equation or d operators or something like that. In each of these cases you have found that the solution to the differential equation is obtained in terms of known elementary functions. Like e to the power minus alpha x or like this. But in mathematical physics, that is in mathematics and physics, one often encounters Laplace's equation, Poisson equation or wave equation, which all are partial differential equations. When one wants to solve this differential equation, generally one encounters a second order linear homogeneous or inhomogeneous differential equation. In this course of lecture we shall concentrate only on homogeneous equations. These homogeneous equations are this homogeneous equation which arises from the solution of the Laplace's Poisson or wave equation when they are solved in coordinate system other than Cartesians. This differential equation that we face cannot be solved by the elementary methods, that is to say the solution cannot be obtained in terms of known elementary functions. Then one applies a Taylor series or Taylor series type expansion method and the solution is obtained as an infinite series. If we apply this solution to represent any physical quantity, then the solution must be finite. So one needs to test the convergence of the infinite series, and ultimately we should have a solution which is convergent in the domain of interest. Sometimes it is found that there are some parameters involved in the differential equation which are to be chosen so that the infinite series becomes a polynomial, or there are other examples where the solution is still obtained in the form of infinite series but is convergent. Such solutions are known as special functions. There are a large category of these functions. They are differential equations, the Legendre differential equation, the Hermite differential equation, Bessel differential equation, Laguerre, Chebyshev hypergeometric differential equation, complete hypergeometric functions like this. So our aim is to solve a linear second order differential equation. Homogeneous differential equation. The form of this such equation is P0 of x y double prime of x plus P1 of x y prime of x plus P2 of x y of x is equal to 0. Firstly, it is why linear, because there is no product of y or its derivative, so it is linear. So when the differential equation involves terms like y square or y times y prime or y double prime y, etc., these are called nonlinear differential equations. So in that sense the differential equation is linear. It is second order because the highest derivative of y involved is 2, so it is second order. and there is no term in this differential equation which is free from y or its derivative. So this is that's why it is homogeneous. Let us consider the differential equation x double prime plus twice bx prime plus omega 0 x is equal to 0, as you have encountered in the case of damped oscillator. It is homogeneous equation because the terms are all the terms involves either x or its derivative. We consider the case of forced damped oscillator. Here this term is free from x, so it is inhomogeneous differential equation. Inhomogeneous differential equation. So we are considering this. Firstly, as we have said that there are a large category of such equations which cannot be solved by the elementary and technique known to you till now. So there are two methods which are very close to one another. One assumes the y to be in a form of infinite series. Now the basic idea behind this expansion is the Taylor series. For Taylor series, Taylor's expansion of a function of an function about a, we have f of x So here we call the expansion is about x is equal to a. So if we want to solve this differential equation using a similar expansion, actually one writes y is equal to y of x is equal to summation over k is equal to 0 to infinity ck x minus a to the power k. Sometimes k and sometimes one use another factor m. If there is no m, it is called power series method. We will come to this later on. So this expansion is about x is equal to a. So we define some relevant quantities referring to the point A. Firstly, what is the regular point? Till now, we haven't said anything about the expansion, about the point of expansion in solving differential equation. Here we come to definition of regular point. Regular point of this differential equation. This is the definition. If at x is equal to a, p0 of a is not equal to 0 and p1 at a and both p1 at a and p2 at a are finite, then x is equal to a is a regular point of 1. This we call equation 1. So there are points which is not regular. Let us give an example. Consider a differential equation, this. This is a differential equation. This is known as Legendre differential equation. You see that at x is equal to, so this is P0. P0 is 1 minus x square, P1 is minus 2x, and P2 is alpha. At x is equal to 0, P0 is 1, P1 is 0, and P2 is alpha. So x is equal to 0 is a regular point. It is a regular point. At x is equal to plus minus 1, P0 is 0. So it's not a regular point. So x is equal to 1 is not a regular point. We call it singular point. So I am coming to the definition of singular point. Any one or both of P1 of A and or P2 at A are non-analytic. Then x is equal to A is a singular point of differential equation 1. When the equation we encounter a singular point, it is at a singular point we rewrite equation 1 as I have not written the argument x here. This is equation 2. So we write it. So this is the alternative form. You see that Q1 is simply Q1 of x is simply P1 by P0, and Q2 if x is equal to P2 by P0. When P0 is 0, then there is a possibility that both Q1 and Q2 are divergent, that is non-analytic. There is one way out. If P1 happens to be 0 too, then it is a finite, Q1 would be finite. Now we say that what is the regular point? Then the regular definition of regular point is that at x is equal to A, both Q1 and Q2 are finite, then it is a regular point. So at regular point we add here both Q1 at A and Q2 at A are finite. So what is the definition of singular point in terms of this? At x, if x is equal to A, be a singular point of 2, then either Q1 at A or Q2 at A or both are non-analytic. This is the definition of singular point. So we have stated singular point in terms of P functions. So this is the definition of singular point in terms of P function, and this is the singular definition of singular point in terms of Q function. If the point under consideration is a singular point, then there are two types of singularity. The one singularity is called the removable singularity. Another type of singularity is called non-removable singularity. So to define that type of singularity, we define the function like this: x1 of x and x2 of x is equal to Q2 of x. Now we study the behavior of x function as x tends to A. So if this is removable singular point, at x is equal to A, but both x1 and x2 of A are finite as x tends to A, then x is equal to A is a removable singular point. Removable or non-essential or regular singular point. So this is the definition of removable singular point. At a removable singular point, any one of Q1, Q2 or both may be divergent, but x1, x2 are finite. Then it is a removable singular point. And for non-removable singular point, either one, x1 or x2 or both will be divergent. So finally, let me check whether this part of the board is readable or not. Yes. For non-removable singular point, if as x tends to a, either x1 or x2 or both are divergent, then x is equal to a is a non-removable or essential or non-regular singular point. So this is all about the singularity analysis of a differential equation. So let me first work out the scheme. First we have a equation in this form, or it may be in this form. If it is in this form and the point under consideration is A, then check whether P0 is 0 or not. Then we see if P0 is not, P0 at A is not 0 and these both are finite at that point, then it is a regular point. If any one of these three conditions are violated, then we go to the singular point. Once we come to singular point, we write the equation in this form. Then at singular point, either q1 or q2 will diverge. Then we go to the x functions and see what happens. Although q1 or q2 may be divergent at x is equal to 0, what is the fate of x1 and x2 function? If both x1 and x2 are finite at x is equal to a, then it is a removable singular point, and if not, it is an essential singular point or non-removable singular point. So we make the summary of it, and we shall, in the next class we shall consider the few examples on the singularity analysis. This is for your information that if the point under consideration be either a regular point, then a simplified simple power series method can lead us to the solution of the differential equation. And if the point under consideration is a removable singular point, then a modified version of the power series method can be applied. Can help us to find the equation. So the summary is P0 y double prime plus P1 y prime plus P2 y is the differential equation, or it is written as or it may as well be written as either definition. So for regular point, for singular point, or anyone for removable singular point. This in terms of Q, it is the alternatively removable singular point as x tends to A. Either x1 or x2 as x tends to A. This is the summary of the singularity analysis. So if you are given a differential equation, you check either the point under consideration is a regular or not. If it is irregular, then define the function in terms of either q's or in terms of x. For removable singular point, both x1 and x2 are finite, and for non-removable singular point, either x1, x2 or both diverges. In the next class, we shall consider few examples of physical interest, and will analyze the singularity of each of the differential equation